Hello, welcome to another Teacher Tobin tutorial. We're going to be exploring topic 3 of the Computer Science GCSE Edexcel specification, and the first main chunk of this topic, which takes up one of the larger aspects of the topic itself, is system architecture, which is 3.1.1 and specification mapping. And there's a lot to unpick here, so this will be a longer video than normal. And it really gets to the heart of what a CPU is, instructions, all sorts of information. So if you can get through this, you've got through probably the trickiest part of topic 3, I would say. So the image you can see here is a photo of John von Neumann, and he created this concept called the stored program computer. Rather than having a computer that just does one specific task, he could create an architecture where you'd have different instruction sets in primary memory, which could be loaded up to perform different tasks. Now, of course, that's how modern computers essentially work. Now, there are different architectures available to learn about, Harvard, for example, but for Edexcel, you only need to know this one. And it's linked to some other concepts about how CPUs get those instructions, called the fetch, decode, execute cycle. So we'll take it step by step. John von Neumann, he created the stored program computer. So if you see that word in the exam, it will be about his ideas of stored programs. Now, the CPU, the central processing unit, it continually, and this is based on the sort of von Neumann idea, it will continually fetch, decode, and execute instructions. And all those instructions are going to be loaded onto, in fact, I'm going to draw a little primary memory thing here. So this will be our RAM. And don't worry, we'll talk more about what primary memory is in another video. But we've got a location in our RAM, and we could have data stroke instructions here. So we might have, just for simplification purposes, we might have different locations, and there could either be, say, a number, or there could be an instruction like load 3. Let's say there's a number in there as well. And the CPU, the central processing unit, is continuously going to look at the RAM, the primary memory, to find out what it should do next. And inside RAM are all sorts of different processes that are going on for different programs and utilities. And sometimes they might be concurrent as well. I mean, a lot of CPUs now have what we call different cores, so they can multi-process. They can do tasks at the same time. For the rest of this particular video, we'll just assume that this is a single core processor, just so that it doesn't confuse you too much. So a CPU will be doing one thing essentially at a time in order. Now, there are different components of a CPU, and there are also some important concepts, like, for example, clock. Each computer will have a clock which determines how many of these fetch, decode, execute cycles we can do per second. So the measurement of that will be in hertz, and that's per second. And typically you might find, let's just say a modern computer might be 3 gigahertz or 5 gigahertz, 3 to 5 gigahertz. So that means it can carry out between 3 to 5 billion cycles per second. Okay. So every second that CPU inside your computer, it's like the brain in Chinese, it's Jian Now, it's like electric brain. That central processing unit is processing up to, if it's a 5 gigahertz machine, 5 billion instructions per second. So in here we might have 5 billion instructions, and it's going to do those just in 1 second. So we're going to obviously slow this down considerably and have a look at what's going on. And we're going to have a look. We've got some exam questions to look at as well, and we're going to go through the fetch, decode, execute cycle. But the fetch, decode, execute cycle, you've got to make sure it goes this direction, and it'll go round and round again once it's done. So fetch, then decode, then execute. So it'll fetch an instruction from the memory, figure out what should I do with it. Okay, load 3, what does that mean? Oh, I need to load from location 3, and then it will execute that. And it will continually do those 3 things over and over again until it's exhausted all the instructions it needs to. And there are lots of components of a CPU, so let's just have a look at what a CPU is. I mean, this is a central processing unit, and inside here there's going to be a section called an ALU. And that will stand for, let me change the colour. I'm going to spell it right. Arithmetic Logic Unit. Essentially a calculator. It's just a giant calculator. A special type of calculator inside the CPU that can process logical instructions using combinations of gates. And it can do arithmetic. So that's in there. We also have what we would call a control unit as well. And that's going to interface with peripherals, input and output devices, all the things that are connected to the computer. So I'm going to put a little label there. Control unit. So these essential parts of the CPU, but there are also things called registers, and registers are really fast bits of primary memory that are actually inside the CPU. Now the CPU might have an area for cache, which you won't get asked about in the exam. It won't be in there, but the CPU does contain cache, which is essentially special types of memory that it can use for repeated tasks. It makes things more efficient. What you do need to know is that there are different registers that hold different things, and different what we call buses which move that information. So, so just pay attention to this next bit. I'll zoom in a little bit. So we'll have what we call, I'll use red again, an MAR, which is a memory address register. So memory address register. And it's a super fast acting bit of memory. We're going to have an MAR. We're also going to have what we call a program counter. And that does not stand for personal computer, that's program counter, which keeps track of what we should be doing at any particular time. And don't worry, I will talk to you about how these all work together very soon. And then we're going to have an MDR, and the way to remember these is the M for memory, and so I'll put memory data register, okay, and that will work with, I'll tell you what, I'll just make a little separate little section here with something called the accumulator. And the accumulator, I'll change the colors there, will interface with the MDR. And we'll see how the accumulator works, but essentially the way I used to view it is like a little piggy bank where you can put information in to get it out later. So we might accumulate numbers, for example, so we can do arithmetic with them later. And all of that's going to interface with main memory, of course, our main memory. And we'll talk about how the channels work in just a second. Let's just continue with the registers because there's one more. A CIR, current instruction register. Okay, the current instruction register. Yeah, let me use different colors for these arrows. The CIR is going to talk to the program counter. CIR is going to go this way to the MAR. Memory MDR is going to go this way. All of these are essentially kind of in one place. Yeah, we've got our control unit and our address bus, which is going to go to our main memory. So the main memory, which is our RAM, is over this way. We've got a control bus, and then from the data here we've got a bidirectional data bus. Bi as in two, directional. Good. There's a lot of information there, and I'll explain in the next part of this video more clearly how this actually works. But just to show you, there's a lot of stuff going on inside the CPU, and unfortunately we do actually need to know in fairly detailed terms how things actually work. So I think the easiest way is to actually just go through some instructions. I think that's the easiest way of figuring out how this all actually works. So we've got the fetch, decode, execute cycle on the left hand side, top left of this little slide. And just for this would be RAM. This would be primary memory, a stick of RAM that's next to the CPU. And then we've got all of our registers: memory address registers, data register, current instruction register, control unit, accumulator, and ALU, which is that calculator, and the program counter. So let's just go through the fetch, decode, execute cycle and see how this would actually work in a real sort of analogy example here. So we've got a mnemonic, which is a English way of remembering something. Assembly language. The assembly language uses mnemonics to help understand what instructions there are. In reality, it would just be load would be given a binary number attached to it, and it would be a long string of binary numbers. But for the purposes of making this easy to understand, and sometimes you see these in the exams, there might be mnemonics here, and load would be equivalent of an instruction in assembly code language. So we've got, let's say, our first thing in our RAM, which is on the address 0. So let's have a look. The program counter contains the allocation of the instruction which has to be fetched. Okay, so what's the location, the allocation? At the moment it's 0. And then, using the address bus, the content of PC is copied to MAR. So we copy that 0 onto the memory address register. Okay, so the address is here. This is the location. It's just like having a normal address of where you would be, like your home address. And then it says the instruction at a particular location is copied. So, okay, what's the instruction? instead of, you can have in here, you can have either two things. In this, it would be either data or instructions. And you can see these, this is just data, and store, add, and load are instructions. Okay, so you'll either have data in there or instructions. And all your coding or your Python or your higher level languages eventually just come down to a whole load of sequential instructions, a bit like this. So even your loops and everything else, they all become a whole string of instructions like load, add, store, and there are other ones as well. So the okay, let's get back to the MDR. So the instruction of that location is contributed to the MDR. That's fine. Oh, sorry, the load for. That's what's in there. Load for. That's the instruction. And then contents of the MDR is copied to the current instruction register. Now, the computer's got to keep track of what it should be doing at any given time because our MDR might update to something else. But we want to keep track of what the actual instruction is before our fetch, decode, execute cycle is done. So we fetched, we found what we should be doing, the location of it, what the instruction is in there, and we stuck it into our current instruction register. And then at that point, what happens is our 0 gets incremented to a 1. So it's essentially saying, look, once we've finished with the first thing in address 0, once we're done with that, we're going to go to the next one when you're ready. Obviously, we haven't actually executed the instruction or even decoded it at this point. We don't really know what it is yet. But once we've done all that, we know where to go next. Okay, so the control unit is then going to have, so our control unit's got to decode our instruction. It's got to decide, what do we do with load for? What is this? What do we need in order to accomplish this? Okay, so in order to load for, we need to be pointing to address 4 and then load the data that's in there. So it doesn't mean load the number 4, it just means load position 4, and it happens to be the number 3 in there. So what's going to happen there is our memory address register is going to change. Let me change the color there. It's going to change to 4. And the data that's in there is going to change to 3. And to execute this, we need to be taking that number and putting it somewhere meaningful, because we obviously are loading it for a reason. So we're going to be putting it into our piggy bank, our accumulator, which accumulate data essentially, so that we might use it later on. And then essentially what we're done with our cycle there. Fetch, decode, execute cycle is done. And we have the program counter already on 1. So it tells us what we should be doing next. And in this case, we should be in position 1, we should be looking at this instruction, add 5. Okay, so let me just clean this up a little bit. So the MAR is going to let's just remove this for a second. So using address, the contents of PC is going to be copied to the MAR. And then the instruction at that location, add 5, is added to the MDR. Our PC gets updated to 2. So once we've decoded and executed our add 5 instruction, we'll know what to do next. Just remove this for a second. And then the contents of the MDR is added as well. I did that in a slightly different order anyway. Um, that should have gone to that first, then PC is updated. But anyway, it's not going to make a big difference. Instruction is decoded. So what is our add 5? So if we're adding location, we're essentially adding what's in location 5. So this control unit is going to say, oh, if I'm adding stuff together, I probably need to use the ALU, my arithmetic logic unit, to do that, because that's the best tool for the job. So we're going to then be looking at location 5 and what the data is in there. So the memory address register is going to change to 5. The MDR is going to be 6 because that's the data that's in there. And the accumulator is going to be saying, okay, well, we've got 3 already. Sorry, the ALU is going to look at the accumulator, say, okay, we had 3 in there and we're adding 6 together. And the sum of that is going to be 9. And that's what is going to be put back into our accumulator as we're executing this instruction. So there's the decode bits up here, control unit's deciding what to do, where to put it, and we're executing the instruction by adding those things together using an arithmetic logic unit. So I'm just going to tidy this up, and I'll keep everything, but I'll just put 9 in our accumulator. And the PC already updated to 2, so we know what we need to do. What's in location 2, what the data that's in there, the instruction, store 6. Okay, so that gets copied to the current instruction register because we need to keep track of what we should be doing by the end of this. Then our PC gets updated to 3. Now it doesn't know that there's nothing there. It just knows that we would be doing the next thing afterwards, and once it gets there, it will realize there's nothing else to do. But the PC will get updated, the program counter, and then the control unit is going to say, what do I do with store 6? Well, I need to. There's a free space in the memory for that, so the memory address register is going to change to 6. There's no data in there yet, but we're going to be storing whatever's in the accumulator into there, so 9 will get stored in there. And this might have started out as a simple Python program where it just could be like A equals 3, B equals 6, and it might just be C equals A plus B. But eventually your high-level program is going to get translated to an assembly-like code, and then eventually to machine code, which will just be binary. We'll talk more about what low-level languages are in a different video. Let's do some exam-style questions, so we can get used to these, what you might see in the exam. So we've got CPU contains a number of components. It sure does. I mean, we've covered a lot of ground there. Carries an instruction from main memory to the CPU. So the data in data stroke instruction area. What's the bus? So the bus is, think of an actual bus. It allows. There are 3 buses you need to remember: data, controller, and address. And obviously, as you saw when we went through the fetch code execute cycle, if we're using the address bus there to send the contents of the PC, because it's to do with memory address register, so it makes sense. Data register, data, and control unit, control. So it carries an instruction from the main memory, which is RAM, to the CPU, it's going to be, out of the 3 buses, let me change the colour, the data bus. I think let's get a better pen as well, data. So the 3 buses you need to know, and it carries the memory location of a piece of data. So you just got to remember that the address in our RAM is there on the left hand side. And if you couldn't remember control, there's only 3 to choose from there, so you put control in, read signal to the main memory. So I'd remember those 2 first. I'll be able to put that in. Identify the component inside the CPU that stores data. Okay, so the registers are the fast acting bits of unit inside the CPU, so don't get caught up with the language there. Yes, main memory does store information. There is data in here. This is main memory, this is our RAM, but it's not inside the CPU, it's next to the CPU. You can update the RAM of your computer. ALU is inside the CPU, but it doesn't store data in that. In fact, it sort of does store data in a way, but it does not. What they're getting at is registers are the fastest acting primary data medium. You've got RAM, you've got ROM, and even faster than that and lower level is our registers. They're inside the CPU, super fast acting bits of storage which hold data for a very short amount of time. So registers the only answer really there that we could possibly have. Nice easy question here. Fetch, decode, execute. You need to remember that order. Fetch, decode, execute. That's a really nice easy 2 marks there. Good. Identify the hardware component that carries instructions from memory to the CPU. So instructions are also in the same place as data. Okay, the address is over here in primary memory. It could be all the order of things, and it could be like load 1, right? Just like we did in our example. So there's either a number in there, some data, or there's an instruction. Load is an instruction. So the data bus would take the data from there and transport it around our CPU. State the component of the CPU that carries out additions. Okay, well, you could put ALU in there and get the mark, but if you want to be really careful, you could just put arithmetic logic unit and type the whole thing out. But you probably get, I mean, I can't imagine why they wouldn't give you the mark if you just put ALU in there. Good. Let's have a look at this one. The components, this is nice and straightforward. 3 marker. It gives you one of the buses already, so you just need to remember 2 of them. Now, a bidirectional bus here is the data bus, so already I'm going to deduce that that's the one for there. And that's really what they're testing you on, is can you remember which one's bidirectional? Now, slightly confusingly, yes, you can see that the control bus is bidirectional too, and in some of the notes, they don't make that super clear in certain GCSE notes, but as a rule, data bus is always going to be bidirectional. Bias means it can go both ways. It makes sense that data can go both ways, doesn't it? That you could take some data and put it back. And the address bus is going to be this one. Now, the clock is going to be 1 arrow pointing towards the CPU. I mean, technically speaking, I guess you could probably put it to the control unit. I think they'll give you the mark if you just pointed it, but I'll just to be careful, I would put the arrow pointing into the middle of it to cover all bases. And remember, the clock determines how many things we can do every second. 5 gigahertz personal computer, 5 billion things each second. Now, all of them are done sequentially. They're all done in order, just very quickly, except if you've got a multi-core processor, and you might have I don't know, you might have a Mac M2 chip or something, and you might find that it's got essentially 8 different processors in there. So you might be able to do 8 different things concurrently. So it might be able to do video processing, graphics, sound, all of that as parallel processes. So modern CPUs are able to multitask very efficiently. Now this is going to be a tricky question. I think it already looks a little bit tricky for my liking, but let's try our best to do it. So here's a representation of the contents of main memory. So rather than having the sort of simplified version I did, well, let's just say that's 0, and that is 3 in binary, and that's 4, and that's 5. Okay, so already there's just lots of little confusing, annoying things about this, which I don't like. But this is primary memory. It's going to be RAM, and it's going to be interfacing with the CPU. CPU is going to be over here. Remember, it's outside of the CPU. And the value, well, instead of just saying value, you should remember that it'll be either data or instructions. Now, we don't know what they are. We don't know what 12 means in this case. We won't need to know, but I'm just putting it down just in case it helps us. Just converting them. Draw a flowchart to show the process required to read the contents of memory location. Okay, so it wants you to look at this one here into the CPU. So how are we going to read that memory location? You must include in your response the buses used. Fine. So what I would do here, I'm going to write down the 3 buses. I'm going to write them down because this is a 6 marker, and I'm sure if they're asking you about the buses, it's going to be half the marks. 1, 2, and 3, and then the contents of each bus is essentially the other 3 marks, isn't it? That makes logical sense. So we've got to remember our 3 buses and what they do. So the address is this column here. So we can say if we're making a flowchart. Okay, so flowcharts always start with a start, don't they? And then we have an arrow going down, and we have a process. What's our process? The process is going to be 0100 added to address bus. And I think that's a mark. I think there was 2 marks there already, because I've told them the bus that I'm using and the contents of it. So I understand that the address bus is used to carry the memory location. So it's not going to be that bad. And let's go to the next bit. And we'll say signal sent down control bus. All right. Hang on. No. The read signal is going to be in there, isn't it? Read. Okay, and then, sorry, I've got ahead of myself. Then 111 placed on data bus. Yeah, the data bus is only going to have either the data or the instructions, and the control unit deals with what should I do, and we're reading that area of the memory. So yeah, I have to be careful there myself. And then finally, that's it really. We would end that. So yeah, it's quite a confusing question, to be honest, because they're assuming that this is read. It might be some sort of other instruction on there, but we know that we have to see that value. So I think it's just, you don't need to remember all the different operation codes in there. I'm pretty sure that's not in the specification. So I'm quite confident with that answer. Read signal sent down the control bus, and 15.1111 placed on the data bus, and then it will end. I'm pretty sure that's going to be what they're expecting there. Good. I know that was a pretty long video, lots to unpack with that one. That should help, but if you want more about it, let me know. I can always make another video. But I suggest you memorize the buses, because you saw most of the questions are actually about the buses. You don't really get asked specifics anymore about MAR or MDR or CIR. You shouldn't do, because in the 2020 specification they seem to removed like really detailed explanations about that. So I have a feeling that maybe this question here might have sneaked in from the older specification. So apologies if that's, but it's still useful to go through it. But you're not going to be expected to know any operation codes or specific things about the registers, other than what the registers are, MAR, CIR, and MDR, and the buses. Those are the things to remember. And that Von Neumann architecture is about stored program concept and clock speed. Obviously, why might it be desirable to have higher clock speed? Because you can process more instructions per second. That would be, if you had an exam question like that would be the simple answer to it. You can do more things every second. Good. All right. See you in the next video.